Today we'll look into some really interesting problems that we can apply our physics knowledge to. And these problems are those that we encounter in our daily lives. And we never bother to think twice about, what is really underlying those physical phenomena. So anyhow, I thought it would be a fun experiment to look at some of the things that we would uh, have seen over the summer. And then one of the activities people would do is go to a fair, okay, and in this fair they would see a Ferris wheel, and it's very common for people to ride a Ferris wheel. So what happens here is that people would sit in a gondola that goes from the bottom to the top, and then it goes around again and again, and you sit there for about 5-10 minutes and really enjoy yourself. But so the question is, do you wonder about whether the Ferris wheel is strong enough, and what are the forces that are experienced by the Ferris wheel in moving people from the bottom to top and back? So that's the thing that we'll look at today. So for the purposes of this lesson, we will assume that there's a person sitting in a gondola, and the total mass of the person on the gondola is m. Right. And we'll also assume that the radius of the gondola, radius of the Ferris wheel rather, of the Ferris wheel equal to r. Okay. So that's what we'll assume. So if we see very carefully, okay, and especially concentrate on what happens at the very bottom. So there are a couple of free body diagrams. So we'll look into the situation where the gondola is at the bottom and when it's at the top. So this gondola here is attached to the center of the Ferris wheel by a rod, right? And the tension in the rod is what keeps the gondola in place so that it doesn't fly off, right? And we also assume that the linear velocity of the person and the gondola is v. Okay, so that's what we assume. If we see like the free body diagram here, okay, at the very bottom, the weight of the gondola and the person acts straight down, and that equals mg. The tension in the rod keeps the gondola in place, so it acts upwards. So if we look at the very bottom and we write the Newton's force balance, we find that the net force here equals T minus mg, and that's the force acting towards the center of the Ferris wheel. And the force acting towards the center of a wheel is nothing but the centripetal force, so that equals mv square over r. So in this particular case, the T here equals mg plus mv square over r. Okay? That's the interesting thing. So the tension here in the rod equals the weight plus the centripetal force. Okay, so the rod has to be strong enough not only to withstand the weight of the person on the gondola, but also to exert enough centripetal force to keep the gondola moving with the Ferris wheel. Okay, so that's very important. Okay, so now let's look at what happens at the very top. If we see here, at the very top, the rod here is now links the gondola with the center, okay, and it is pointing downwards, right? So the tension in the rod also points downwards. Okay, the weight of the gondola and the person also acts downwards, straight down. So if we look at the net force here, So the net force towards the center is T plus mg equals the centripetal force, it's mv square over r. Therefore, the tension here equals mv square over r minus mg. Okay. So what happens here? There is a condition under which the tension can go to 0 when mv square over r equals mg. So we can cancel out the m's here, and v equals square root of g times r. Okay. Under that circumstance, the tension in the rod can go to 0. Okay. So we see a situation where the tension in the rod is very high at the very bottom. Okay. It can go all the way to 0 depending on how fast the Ferris wheel is moving. So the tension in the rod keeps changing with respect to time. Okay. So that's one of the results that comes out of this analysis. And so the engineers who design this Ferris wheel make sure that these rods can withstand the kinds of stresses required. Okay. Thank you. So let's now look at a slightly different situation. Right. This situation involves us going to the races. So let's say a car race, so to speak, and we take the example of NASCAR. Okay. And if you go to a NASCAR speedway, especially those of us who live in the Midwest, can easily see lots of vehicles, okay, speeding on the tracks. And one of the things you see that the cars not only zip through the tracks, but they tend to slide downwards internally, and they also drift outwards. Okay. The track itself, if you take a look at the track, right, the track itself, essentially looks like this. Right? So here is where the pit area is, and then the cars are moving along this banked area. Okay, so that's essentially what is happening. So let's erase that because I need this for other things. Right? So there are these two situations. Okay, the car tends to slip downwards, right? Okay, down the track, or the car tends to drift upwards. So essentially, if the car is going too slowly, okay, it tends to slip down, okay, along the track, or it tends to drift upwards up the track if it's going too fast. So there is a narrow range of velocities that are permitted for the car. Right? We assume that the radius of this track here, okay, is r, and the coefficient of friction is mu. Okay. So let's take a look at the forces. So in this particular case, the weight is acting straight down, right? And since the car is thought of as slipping down, the car is thought of as tending to slip down, the friction force tends to oppose that, right? And the normal force keeps the car on the track, and it's perpendicular to the track. So if we see here, the horizontal force, the net horizontal force that's acting inwards towards the center of the track is what provides the centripetal force. Okay, and if we'll take a look at that, right, so the net horizontal force is essentially it is should equal the centripetal force. So it's mv square over r equals, okay, this is Fn sine theta, okay, because this is being theta. So the component of Fn in this direction is Fn sine theta, Fn sine theta, and then from that we take away this force, which is essentially the friction force resolved in the horizontal direction, which is friction force times cosine theta. And friction force essentially equals mu times Fn. So we can write this as minus mu times Fn, okay, cosine of theta. Okay. Now the other condition is that for the car to remain on the track, the vertical forces should balance out, right? So now what is happening here is that the frictional force in this direction has a vertical component, right? And this is frictional force times sine of theta, okay? And the vertical component of Fn is Fn times cosine of theta. So, and that should equal the weight. Okay, so let's do that. So here we can write the weight mg equals Fn times cosine of theta plus mu times Fn sine theta. Okay, so this is equation 1, that's equation 2. So what we do here is we divide 1 by 2. So mv square divided by r divided by mg equals Fn sine theta minus mu Fn cosine of theta divided by Fn cosine of theta plus mu Fn sine theta. Okay, so one thing we do see here right away is that the m's cancel out, the Fn's cancel out, and we can also divide both the numerator and denominator by cosine theta. Okay, so essentially we end up getting v square equals r times g times tan theta minus mu divided by 1 plus mu tan theta. And then if you were to take away the square from the left, we can put a square root on the right side. And so this is the minimum velocity with which the car needs to move in order to stay on the track without sliding down. Okay, so that's the minimum velocity that the car needs to move with in order to not slide down. Okay, so now let's look at the situation in which the car tends to drift upwards. So the friction force resists that, so it's acting in the downwards direction. Okay, it has got a positive component in the horizontal direction. Okay, and that horizontal component is friction force times the cosine of theta, because this angle is theta. So in this particular case, if we write the horizontal force is the centripetal force that keeps the car on the track. That's mv square by r, that's equal to Fn times sine theta plus frictional force, that's mu Fn times cosine of theta. Okay, so in this particular situation, we see that the normal force hasn't changed at all. Okay, so we don't need to worry about that. So now the thing is that with the friction force acting downwards, it has got a component in this direction, and then the normal force component in the upward direction needs to subtract the downward component of the friction force, right? So and the net force downwards is the weight. So the weight here equals the net upward force. Okay, so because the forces in the vertical direction need to balance out, it is Fn times cosine theta minus mu Fn times sine theta, right? So if this is equation 1 and this is equation 2, when we divide the two equations, that is equation 1 divided by 2, we get mv squared divided by r equals Fn sine theta plus mu Fn times cosine of theta divided by Fn cosine of theta minus mu Fn sine of theta. And we divide here on both sides by cosine of theta. So what we see here is, there's one more term that I forgot to put in, divided by mg. Okay. So now the m's cancel out here, the fn's all cancel out. So we can rewrite this expression here as v square equals r times g times tan theta plus mu divided by 1 minus mu times tan theta. And if we take out the square, okay, we can put this in the square root on the right, and that's the expression for the maximum velocity that the ramp can tolerate, okay, without the car drifting upwards. Okay. Now, in the previous exercise, we observed that there is a minimum velocity as well that the car needs to have in order for the car to not slide downwards. Right? So here the car needs to have a velocity that's in the range, the maximum and minimum. Okay, so we need to have the velocity, okay, to be in this particular range. Okay, so let's see what happens here when mu is 0. Okay, when the mu is 0, for 0, we have Vmax. Okay, so in this particular case, this term goes to 0, this term goes to 0. So we have Vmax equals Rg tan theta. Okay, and in this particular case, this goes to 0 and that goes to 0. So Vmin is also equals the same thing. Okay, so when there is a zero friction, then there is no difference between the minimum and the maximum velocity. Okay, so there is only one velocity at which the car needs to be in order for it to not slide either way. Right? So let's look at the situation where theta is 0. When theta is 0, then tan theta is 0. Okay, so both these terms are 0. So we get Vmax equals mu times Rg, and we take the square root of that. Now the interesting thing is that there is no Vmin here. Okay, there is no Vmin because the only way the car can slide is outwards, okay, away from the track. Okay, and Vmin here is not defined because when theta is 0, tan theta is 0, this term is 0, we get a value of negative mu. Okay, is not defined. Okay, so that illustrates to us the power of this analysis, right? And it also shows us what happens, right, when the friction in the track is very less. And you can easily see here that the driver of the race car is constrained to move along a very specific velocity in order for the driver to not go up or down, right? And so this can happen in the conditions when when it's raining a lot, when the track is slick because of ice or snow. right? So people have to drive much more carefully. Okay. Now, what happens when theta is zero? The theta is zero is a situation where we see in Formula One races, okay, where it is much easier for the car to drift, okay, drift outwards. So the cars have to be specially built in order to not drift. Okay, so that's a very special case, and the cars have to be built so that they withstand the kinds of situations that they are put into. So I hope this kind of helps you to understand what is involved in car racing, okay, and then what inputs the drivers of these races need to process in order to uh, not only drive safely but also win the competition. I hope this helps. If you like this video, please press the like button and subscribe to this channel, because you'll get a lot more fun videos like this. Thank you.